You're listening to Worth Electronics' What's Up Radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and our Worth Electronic technical specialists who are going to shine a light on some interesting topics such as energy harvesting, wireless power transfer, EMI, and much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with the Worth Electronics What's Up podcast. Today's discussion centers around the Universal Serial Bus, commonly known as the USB. We'll be discussing the interface, but from an EMC point of view, and talk about the technologies, hardware and components, PCB layout, and more. Now, the USB specification defines the mechanical and electrical characteristics as well as the protocol layer of the interface. The cable and connector are precisely defined. USB defines two types of hardware, hubs and functions, as well as terminal devices. So in theory, up to 127 devices could be linked together in a star bus topology, where the only limitation is this 7-bit address. Connections are possible between the hub and function or terminal device, or between hub and hub, by which direct connections between terminal devices are not possible. USB is a differential, bi-directional serial cable bus. The differential non-return to zero invert signal is transmitted asynchronously between the ports. The max cable length here is 4 meters, and the cable contains 4 wires, 2 for the twisted data pair and 2 for the supply voltage of the terminal devices and a ground. The data rate is between 10 kilobits per second and 480 megabits per second in one of 3 possible modes. First, 10 to 100 kilobits per second for slow data transmission, like a mouse or keyboard. The signal voltage here is between 0 and 0.3 volts. Second, 0.5 to 10 megabits for medium data transmission rates, where the signal voltage range is between 0.3 volts on the low end and up to 2.8 volts on the higher end. And finally, 25 to 480 megabits for high data transmission. This is defined as USB 2.0 with a max possible rate of 480 megabits per second. At high data transmission rates, it's necessary to terminate each of the symmetrical conductor pairs to ground with a 45 ohm terminal resistor. Here, the cable impedance must be 90 ohms plus or minus 15%. Now, originally, USB was intended to replace the serial and parallel interfaces in IT. But now, USB has become established not only in the IT domain, but it's become an absolute necessity in many other fields of application, like home audio and video, mobile IT, uploading data to PCs, software upgrade, data downloads, medical devices, and even in the automotive industry for MP3 music. USB is a network with a star-shaped topology. All other USB terminal devices branch out from the host controller. A USB terminal device represents the bus connection, whereas a USB hub can branch to another hub or to terminal devices. Every other USB hub can represent a branching point until the max number of addressable devices is reached. This proves that a complex network structure can be built up with a USB, but it also clearly shows that this structure has to be paid special attention with regard to EMC. USB devices as standalone devices, such as without hub, without further branches, they can display EMC weaknesses and only just meet the demands placed on them. If these devices were in a more complex structure, they could no longer meet the requirements and could potentially throw errors with drives, dropouts with cameras, writing delays with keyboards. The list continues on. We'll be discussing this a little bit later. But for now, let's dive into the hardware and the components of a USB. Receptacles and plugs can have different sizes with USB depending on their use in cameras, video devices, or IT. The USB hub and terminal device connector can also differ in their form, but the pin assignment is always the same. You can download our image of pin assignments of the USB interface by clicking the link available in this podcast. Our second download shows you how the USB cable should be structured. The cable has 4 wires. This includes the data wires, which are 28 American wire gauge, also known as AWG, and the supply wires that are 20 to 28 AWG. This defines the diameter and copper resistance. The high-frequency conductor parameters result from the further structure. The 2 supply wires are untwisted, but the data wires are twisted around one another. This results in the differential mode impedance of 45 ohms or 90 ohms against ground. The cable shielding should have a shielding braid with an area coverage of at least 65% and also an aluminum shield. This is because double shielding is intended to guarantee high shield attenuation and consistent wave impedance for the cable. We like to think that all shielding is created equal, but there are many black sheep on the market, some of which only have an aluminum shield, and even this consists of a foil that's only metallized on the one side. Now with this structure, that shield leaves a gap over the entire length of the cable, so the shield attenuation hardly makes values over 15 decibels, rather than the common greater than 50 decibel range. But hey, it is cheap. The cable length must not exceed 5 meters. If you need a longer length, then hubs have to be connected in between. Because of the high flexibility in the application and the high data transmission rate, special requirements need to be taken for the circuit design and the interface construction. Chip manufacturers know the problem of high data rates and the EMC requirements. But not only the chip design needs EMC consideration. The complete circuitry concept has to be developed with a view on EMC. Because of this, the circuit concept, the layout, the filter concept, and construction with the housing and connectors all have to be coordinated. This certainly takes more effort in the development phase, but trust us, it pays off in the long run, not only in higher quality, but also in lower production costs. Good engineering doesn't make products more expensive, but given the same quality, it does make them cheaper. So what does EMC have to do with USB interface? Now, before taking a closer look at this, we need to define an equation. EMC equals assured functionality. EMC is not simply nice to have to meet legal requirements. EMC, in our example of USB, means low interference radiation. This means a well-matched symmetrical interface with optimized filters does not radiate. Through matching, the useful signal has the required quality factor Q. So we also achieve the required signal-to-noise ratio and high interference immunity. By symmetrizing the useful signal and using additional filters with overvoltage protection, as well as interface jacks offering high levels of shielding attenuation with a relevant high design quality housing, the interference immunity is considerably increased against transients and other inductively and capacitively coupled interference signals, and voila, functionality is ensured. What EMC phenomena do we have to consider in the development of a product with USB? And what are the most critical phenomena? Well, these include interference emission, its interference field strength, interference immunity against ESD, also known as electrostatic discharge, and interference immunity against FTB, fast transient bursts. As we previously mentioned, there are numerous application areas for USB. Every application area has other standard EMC requirements, but let us consider our equation again. EMC equals assured functionality. Functionality must always be ensured, and experience shows if functionality works, then EMC also works, regardless of the application area. Now we're going to check out USB circuit design step by step and examine design points to be considered. The USB interface is a bidirectional symmetric interface. You can see our example presented called Figure 3 in our attachment. Symmetrical transmission techniques have numerous advantages in terms of signal integrity, which are apparent in lower interference emission and higher interference immunity. For a more detailed explanation of this, view the attachment labeled Figure 4 in this podcast. The following are measurable. First, interference voltage between the signal wires. Next, interference voltage between the voltage midpoint and the reference voltage or the ground and the cable shielding. This means that the USB transmission path can be affected by both differential mode as well as common mode interference voltages. This can be both interference voltages from the interface itself, in this case described as interference radiation, or interference emission, or an electromagnetic effect from the outside in the form of inductive, capacitive, or wave coupling. In this case described as interference coupling, which assumes a certain interference immunity of the interface in order to maintain continued function. In the case of USB transmission, differential mode interference is mainly generated by non-linear signal harmonics due to mismatching and inadequate circuit design. Given asymmetry of the transmission path, for example, the transmitter, circuit board, and conductor tracks, this interference can lead to interference radiation and impairment of signal quality. Common mode interference arises from parasitic coupling in the circuit environment of the USB controller, which can usually be found from capacitive coupling on the USB signal with rising interference frequency and increasingly in amplitude. These interference types, however, are found on both USB wires in phase and at the same amplitude, and therefore do not impair the useful signal. Asymmetries in the cable or at the receiver often convert the originally common mode into a differential mode interference signal, which can then contribute to signal impairment. Our fifth figure attached illustrates conversion of differential mode to common mode interference due to parasitic coupling capacities. Differential mode data transmission offers a significant advantage over the simple coaxial cable when it comes to the effect of interference on the USB. Depending on the shielding effectiveness of the coaxial cable, a burst couples into the data line and interferes with the data signal. This leads to data or communication errors, which depend on the interference signal length and amplitude. In our attachment called Figure 7, this represents the case of differential mode data transmission, in this case with only a twisted pair of wires. The polarity of the useful signal is shifted from one wire to the other by 180 degrees. The signal difference is evaluated at the input of the receiver. But the interference signal affects both wires in the same phase, so this cannot have an effect as an interference signal at the receiver. Furthermore, in the case of the inductive interference effect, the twisting of the wires achieves compensation of the interference effect. As a result of the symmetrization of the partial inductances of the respective twisted wire, the interference influences compensate each other. It is apparent in practice that interference emissions cannot be prevented, and also interference immunity has its rather stringent requirements. There are a few main reasons for this. First, the inputs and outputs of the USB controller are insufficiently symmetrical. The USB signal displays common mode interference. Next, the layout is not high frequency or EMC compatible. Parasitic capacitances and the lack of wave impedance matching generates common mode interference. Our next reason is the circuit design or USB filter is inadequate. The filters affect the signal quality and/or the insertion loss is too low. Aside from the inadequate circuit design, the interface design, such as the receptacle or housing, may also be inadequate. Poor ground reduces the shield attenuation of the cable, and filters have poor ground reference. Lastly, the USB cable could be asymmetrical, poorly shielded, or it might have inadequate ground connection. The cable deteriorates the signal quality, radiates signal harmonics, and has insufficient shield attenuation towards external interference sources. Some points cannot be influenced, such as the technical aspect of the USB controller and the use of cheap USB cable. This just shows that preventative measures have to be taken. These measures include protecting the interface from the effects of external interference, which can lead to the destruction of the USB controller. Also, measures to limit interference radiation of signals through the cable. Both points can be achieved using additional filters and the USB interfaces. Capacitances of up to approximately 3 picofarads between the data line and the ground are tolerable with USB 2.0. Beyond this, the signal is impaired too much so that nonlinear distortions occur that cause phase shift and attenuation in the harmonic component of the useful signal. As seen in our attachment we call Figure 8, the capacitors C2 and C3, together with the current compensated choke, reduce the symmetrical interference components. The capacitances C2/2 and C3/2 affect the signal. It goes without saying that C2 equals C3. C1 reduces the symmetrical interference components and also affects the useful signal. Its capacitance should be less than 4 picofarads. The values depend strongly on the properties of the current compensated choke. Still looking at Figure 8, the choke must have a high degree of symmetry and low stray capacitance between L1A and L1B. Furthermore, the real component of the ferrite permeability, that is, the inductive component, must be low and within the useful frequency range. On the other hand, the resistive component of the permeability, that is, the more complex component, must be high and within the frequency range to be filtered. Transient interference signals such as ESD and bursts can generally be limited with varistors, especially surface mount multi-layer varistors, which are particularly fast and withstand a high level of energy. What they all have in common is their high capacity, which is why they are not suitable for limiting transients at the USB. Our next figure attached is Figure 10, where you can see transient limitation with diodes. Transients are limited against ground both on D+ as well as D- up to the forward voltage VF of the diodes. This voltage is around 0.7 volts for silicone diodes. A problem appears very quickly here, which is why the diode pair on the right in our illustration has 2 red flashes. The signal voltage of the mid-speed signal is up to 2.8 volts. Therefore, the positive branch must be provided with an offset in order to avoid impairing higher signal voltages. The solution here is an additional TVS diode with a limitation voltage of 6 volts that sets the threshold value to around 6.7 volts. This is sufficient for protection. TVS diodes with lower limitation voltages are too slow to limit ESD. Our attachment, called Figure 11 in this podcast, shows a complete circuit diagram of the USB 2.0 filter. Transient limitation at the connection of the supply voltage can be achieved at the same time by using the additional diode labeled D5 in the picture. Even though the capacitance of the TVS diode is low at 5 picofarads, it would be too high for USB. Also in this image, you'll see that VR1 is in series with D3 and D4. However, the capacitance of VR1 reduces the overall capacitance that affects the signal here. So it is uncritical, as D3 and D4 have capacitances of approximately 2 picofarad. As with our previous graph in Figure 8, capacitors are in series with D3 and D4 with reference to the signal. There's an overall signal-to-signal capacitive load of 2 picofarad, and the signal against ground of around 3 picofarad. In the supply voltage branch, there is a T filter with 2 surface mount ferrites and a ceramic capacitor. The loss component of the permeability should rise sharply at around 30 megahertz. The inductive component is uncritical, as no signals are affected. The current carrying capacity is an important parameter which is specified in the datasheets at 20 degrees Celsius, but of course, it should be selected to be adequate for the application. Join us next week as we continue and finish our discussion on USB interface from an EMC point of view. We'll talk about the filter for DC supply, data line filter, and the Worth Electronic USB 2.0 EMC application board and how you can get your own. You are listening to Worth Electronics What's Up Radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Worth Electronic technical specialists. We're going to shine a light on our topics such as energy harvesting, wireless power transfer, EMI, and more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with the Worth Electronic What's Up podcast.